Welcome everybody to a wonderful and also very strange new chapter, quantum physics. We start by giving a brief historical account of late 19th century physics and beginning early stages of the 20th century. This is what needs to be called the crisis of classical physics. This first problem here was actually not the historical starting point, but this is much easier to understand. That's why we begin with it. In the beginning of the 20th century, it became apparent, or maybe even late 19th century, that there must be atoms. This was a long and very difficult process. And a lot of brilliant scientists were mocked for believing in atoms, like Boltzmann, who actually committed suicide. And then, due to J.J. Thomson, Rutherford and other brilliant experimentators, it became clear that atoms must consist of a small positively charged nucleus and electrons somehow being around that nucleus. Now if you try to describe atoms using classical physics, meaning Newton's mechanics and Maxwell's electrodynamics, you run into a very serious problem, because let's assume the electron moves on a circular path or any path, doesn't really matter, has a velocity. Then of course there is the Coulomb force between the nucleus and the electron, attracting the electron to the nucleus. That means there is a centripetal acceleration. A centripetal force. The Coulomb force acts as centripetal force for this circular motion here. So I have an accelerated electron. The electron is a charged particle, and we know from classical electrodynamics, whenever a charged particle is accelerated, it radiates electromagnetic radiation. And then, using classical laws, you can approximate that the electron should lose all of its kinetic energy in a very, very short time span. I think some milliseconds or even nanoseconds, and thereby spiraling into the nucleus, and the atom would be gone. So atoms would be unstable in the first place. So it would never have been possible for hydrogen to develop after the Big Bang, and we certainly wouldn't exist. So this shows very clearly and brutally that the well-established Newton's and Maxwell's laws or theories of classical mechanics and electrodynamics or electromagnetism are not suited to describe atomic or subatomic processes. So we need a completely new theory. This came quite as a shock. And as a little anecdote, when Niels Bohr, the famous Danish physicist who developed one of the first atomic models that actually worked and could predict something about the spectra of hydrogen, he presented his theory, which was very much based still on classical views. So where electrons move on circular path around the nucleus, and then someone from the audience interrupted and said, "Well, Professor Bohr, why doesn't the electron radiate?" And he just turned away angrily and mumbled, "Well, it just doesn't radiate, okay?" This was really a problem to find a new appropriate theory. Okay, the next thing I'm going to describe could really be called the birth hour, or the birth of the new quantum theory. In the late 19th century, a lot of physicists were trying to find a formula describing what is called blackbody radiation. By combining the laws of thermodynamics, the well-established laws, and the well-established laws of electromagnetism. So what is blackbody radiation? We can't go into much detail here, obviously, because we don't know the slightest thing about thermodynamics, but I'm gonna tell you roughly what this all means. Black body is a body that absorbs all the incident electromagnetic radiation, especially the visible light. That's why it's called a black body. Now a decent approximation is the following. You take a round sphere, painted black with a little hole inside. And the inside of the sphere reflects electromagnetic radiation. So you take metal or whatever inside. And through the hole, the incoming electromagnetic radiation gets reflected here inside the sphere, and since the hole is very small, almost no radiation gets out again from the infalling radiation. So this is a model for a black body. It's not perfect, but it works fine. And when this black body here has reached what is called a thermic equilibrium, meaning that he has a constant temperature, then he is radiating away energy in the form of thermic radiation, which includes a whole spectrum of electromagnetic waves. And of course he must radiate away energy because otherwise his temperature would increase if ever more radiation comes inside of it. So in this equilibrium state, this black body has a constant temperature T measured in kelvins, the absolute temperature. And now the problem was to find a formula describing the energy of this thermic radiation that the black body radiates away. Now if you take a black body of a temperature of about 5000 kelvins, which is almost the temperature of the sun, of the surface of the sun, this is more towards 6000, but doesn't matter. Then if you actually measure, the real curve should look somewhat like this green curve here. Here on the x-axis we have the wavelength of the electromagnetic radiation, meaning here shorter wavelength lead me at some point into the ultraviolet region, like for example here would be the visible light from 400 to 800 nanometers. Here would be the ultraviolet spectrum would start here, and here we would go into the infrared region of the spectrum. And now what is actually measured is a rather difficult quantity. It's called the spectral radiance. There are a lot of different quantities. It's kind of confusing, but very, very roughly speaking, this is simply the power that gets radiated away by the black body. Correct definition would be power per solid angle measured in steradians, which is roughly the angle on a sphere, describing angles on a sphere connected to the area of the sphere, and divided by the emitting area in square meters, and divided by the wavelength of the emitted radiation, measured in nanometers. So the correct unit of this quantity would be watts for power divided by steradians times square meters times nanometers. But doesn't really matter, you can roughly think of the power that is radiated away. Now two physicists named Rayleigh, we already know him, Lord Rayleigh, and Jeans found a law. Rayleigh 1900, Jeans I think a little bit later, but it's nowadays known as the Rayleigh-Jeans law, which combined classical concepts, and they ended up with this formula. The spectral radiance, or roughly power, of course depends on the wavelength and the temperature. And they found that by classical reasoning, this should be given by a constant depending on the temperature, actually proportional to the temperature, divided by the wavelength to the fourth power. So if the temperature is constant, this would mean that the spectral radiance would be proportional to 1 over lambda to the fourth power. And this is a big problem known as the ultraviolet catastrophe, because as lambda gets smaller, so mathematically in the limit lambda goes to 0, this expression of course goes to infinity. So the theoretical prediction would be that the smaller the wavelength, the higher the radiance or the power, and for lambda goes to 0, this should actually go to infinity, which is of course completely absurd for a physical theory to give this infinity here. So this was a real problem because the classical theories didn't give the right results. And now the famous German physicist Max Planck enters the stage. Funny story, in the 1870s he was thinking about what to study. First he was interested in music, but then he thought, well, I can't make a living out of that, maybe I should study physics. And the well-known physics professor at the time back then, Philipp von Jolly, a German physicist, told him, yeah, well, in physics, like everything is already known. Some irrelevant gaps need to be filled, but the physics as a whole explains everything in nature, so that's maybe not a good choice. And boy, was he wrong, because Planck, after all, studied physics, and in 1901 he came up with the correct formula for this black body radiation. So we first talk about the formula and then how he got there. So he found that the spectral radiance, or roughly speaking the power radiated away by this black body, is given by this expression here. We have a constant divided by lambda to the 5th power, and then we have this fraction here, and in the denominator we have the exponential function raised to the power of another constant b divided by the product of the wavelength and the temperature -1. Now when lambda gets large, you can make a Taylor expansion of this exponential function and you actually end up with the Rayleigh-Jeans law. So this is contained as a special case, and actually here for large wavelength this gives pretty decent results. So here the red and the green curve, they get closer and closer, which is why this was not so bad only for a small wavelength. But this here turned out to be the correct formula, and it gave very, very good predictions for the curves that were actually measured. So here we see those are only rough sketches, please don't take it too literally. Here again we have the wavelength in nanometers, here the visible spectrum from about 400 to 800 nanometers. Here you have the infrared region, and here you have the ultraviolet region. And if you plot here these curves for different temperatures, you get these. In green for 5000 kelvins temperature, then for 4000 kelvins and for 3000 kelvins. Actually the high points should lie on a curve, so this is, well, as I said, these are only rough sketches. And this actually coincided with the experimental data, so there was no doubt that this formula is correct, and it since became famous as Planck's law of black body radiation. Now the constants involve the speed of light, which is not so surprising because we're dealing with electromagnetic waves which travel at the speed of light, and a new constant which Planck had to introduce first for mathematical reasons, and which is now one of the most famous constants of all of physics. It's Planck's constant, h, and it is about 6.63 times 10 to the -34 joules times second. And it turned out that this constant actually governs all the subatomic quantum physics processes, but Planck didn't know that at all. And here the other constant b involves h as well, the speed of light, and the famous Boltzmann constant from thermodynamics. Now, to derive this formula, Planck had to make a very, very strange assumption that he thought was, in the beginning, was only a mathematical trick, because it couldn't obviously be true, because it contradicted everything you knew about classical electromagnetism. He had to assume that the energy exchange between the electromagnetic radiation field, like here inside this black body, and the oscillators in the wall of the black body, they weren't called atoms yet. The atom hypothesis was still not firmly established, but it was clear there must be some kind of oscillators that can react to electromagnetic radiation and then reflect it. Otherwise, there would be no reflected light or heat or whatever. And he had to assume that this energy exchange is not continuous, but happens discretely or discrete, or as he called it, quantized. What does that mean? That means that the electromagnetic radiation is emitted from the wall or absorbed from the oscillators in the wall, not continuously, but only in discrete packets, which Planck called quanta, singular is quantum, that carry a certain amount of energy. He found that if he used this formula with this newly found constant, then everything works. But as I said, he didn't like it. That means an atom in the wall can only absorb energy of the amount 1 times this amount here, h times the frequency of the respective radiation, or 2 times hf, or 3 times hf. It is, however, not possible that an oscillator in the wall absorbs an amount of 1.5 times hf, or even 3/4 hf, or 1/2 hf, meaning that if the energy is too low, below 1 hf, no oscillators can be excited at all and made to produce or reflect radiation. And to see how absurd that is, we use an analogy, like you take a group of 100 people and measure their height. And then this would be like saying, well, there are people of the height 1 meters 50, 1 meters 75, and 2 meters. In between there is nothing. This would correspond to the height being quantized, which is of course completely, absolutely ridiculous. But Planck found out if he uses this assumption that energy is quantized, then everything works perfectly and beautifully mathematically. And this, without Planck even knowing himself, this was the birth of the actual quantum theory. And then some years later, Einstein in 1905, with a famous paper that later got him the Nobel Prize. Planck, of course, also won the Nobel Prize. And the Indian physicist Bose, and somewhat 20 years later, they actually realized that these quanta are real physical particles, which they called photons. And nowadays we know these are the quanta of the electromagnetic field. So the electromagnetic field is quantized and the particles are called photons. Particles is not to be understood in any classical way, as we are going to find out, because they behave very, very strangely. So this was a short history of how quantum physics came into the world. And before we go on, we actually look at some quotes from the early pioneers or the masters back then of quantum physics, what they had to say about the newly emerging theory. Okay, most of the quotes are in German because most of the physicists actually were German or Austrian. I'm trying to give you a simultaneous translation. So the famous Niels Bohr said, someone who isn't shocked by quantum theory didn't understand quantum theory. Werner Heisenberg, a famous German physicist, said, he who claims he has understood quantum physics didn't understand quantum physics. Then Albert Einstein, as we are going to see, probability is somehow built into quantum physics. Can only make predictions about probabilities. And Einstein couldn't accept this until the end of his life. And he said, it seems hard to look the Lord into his cards. I don't know if this is an English expression, but that he plays dice and uses telepathic means, as the present quantum theory assumes, well, I can't believe that for a moment. Turns out he was wrong. Then Max Born, who actually came up with a probabilistic interpretation of quantum physics, one of the teachers of Heisenberg, said, Die Quanten sind doch eine hoffnungslose Schweinerei, meaning the quanta are a hopeless mess, or even or a hopeless Schweinishness. I think this word exists. I don't know if it is regularly used, but it's Schweinerei means Schweinishness. And then the brilliant and famous Richard Feynman. He was not a pioneer. He lived, he worked in the 1950s, 60s, 70s mostly, but he was a pioneer of quantum electrodynamics. He made the famous quote, I think I can safely say that nobody understands quantum mechanics. That doesn't mean that he didn't know how to manipulate the formulas and make predictions. He knew that very well, but to understand what happens at the core of these phenomena, is pretty impossible. We're going to find out about that. Then Erwin Schrödinger, the famous Austrian physicist and philosopher who found the equation that governs all of the quantum world, the Schrödinger equation, he said, at the moment a new atom theory tortures me or annoys me. If only I knew more mathematics. So be aware, if you want to become a physicist, you will need a lot of math. I'm very optimistic and hope that if I can do it by calculation, it's going to be very beautiful. He actually had to ask Hermann Weyl, a very famous mathematical physicist, to solve his equation that he found. He couldn't do it, but they together solved it, and it turned out it described the hydrogen atom perfectly. Well, a better translation would be maybe, I'm very optimistic about this thing and hope if I can solve the equation, then it is going to be very beautiful. And then about the quantum jumps that you all have heard of, the quantum leaps. He said, if it's going to stay with this damned quantum leaping, quantum jumping, then I regret ever having invested time in the quantum theory. Wolfgang Pauli, also one of the early pioneers of quantum physics, very brilliant mind, worked together with Heisenberg a lot. Physics, translated freely, physics is a mess right now. For me anyways, it's much too complicated, and I wish I were a movie comedian and would never have heard anything about physics. And if someone like him said it's too difficult for me, he was a very, very sharp-minded physicist. I think when he was 18, he wrote a paper on Einstein's general theory of relativity that even Einstein was impressed by. So if Pauli said it's too difficult, then it's really difficult. And then one of my physical heroes, at least when I was younger, Paul Dirac, or Paul Adrian Maurice Dirac, said famously, each photon interferes only with itself. We are going to learn what that even might mean, but it's a very, very famous quote. And he said, it seems to be one of the fundamental features of nature that fundamental physical laws are described in terms of a mathematical theory of great beauty and power, needing quite a high standard of mathematics for one to understand it. And well, this is true. To solve the Schrödinger equation, it's almost never possible to do by hand. You need to simulate it on powerful computers, and it is researchers do it till today to solve the Schrödinger equation for different potential functions. You may wonder, why is nature constructed along these lines? One can only answer that our present knowledge seems to show that nature is so constructed. We simply have to accept it. One could perhaps describe the situation by saying that God is a mathematician of a very high order, and he used very advanced mathematics in constructing the universe. Now, if you think about what the modern string theorist and the modern theoretical physicist actually do, this turned out to be so true. Like, you need all the math you can find to describe the actual physical reality. Okay, this was a little detour, but I think interesting nonetheless, and we are concerning ourselves now to understand what all these quotes mean and why people were so upset with the new theory and how we can make sense of the strange behavior of subatomic particles. Okay, I hope you'll join me for the ride, and I will see you soon. Thanks for watching. Bye bye.